So we left off last time saying we really need to come up with a better way of writing systems of differential equations. And it turns out we probably already know a way of writing systems of equations. And it turns out matrices can be really handy for this. Now, so for some of you, matrices may be that thing you learned about in pre-calc a long time ago, but you don't really know a whole lot about it. For others, maybe you have a little bit more comfort with them. So we're just going to do a real brief sort of look-see at how matrices work. And so if you start off with two simple linear equations, you can think of each one of these equations as a row. And you can think of each of the coefficients of each of the variables, right? The 3 and the -6 in this case, the variable coefficients, as a column. And so if you've got rows and columns, then you have what are called matrices. And so I'm going to write this system as a matrix that probably looks familiar if you've ever done a little elimination method solving of a system of equations. So matrices are usually written inside of square brackets, sometimes vertical lines, but for the purposes of this, we write the row, but only the coefficients. So 3, 2, and 7. And the next row is the next equation. So -6, 1, and 6. And you may see it as there being a little dotted line through here that represents the equal sign. The dotted line is actually not part of the matrix. It's just a visual representation. And for us, we can see that each one of these columns represents those coefficients, and each one of the rows represents an equation. So that 3 corresponds to the top left element, so top row, leftmost column element, and that corresponds to the coefficient for x. Right? So these are the x coefficients, these are the y coefficients, and these are the coefficients for what the equation's equal to. And this thing right here might be used or would be used in an algebra class if you wanted to do something called Gauss-Jordan elimination. And the purpose of this is this process allows the matrix to be manipulated. So it allows matrix manipulation to a solution. Now, this matrix we can manipulate and get an actual solution, but that's not really the point of what we're going for here. If you're interested in doing that and you want to do a little refresher course, you could use, like in your calculator, if you have a TI calculator, this may look familiar, something called RREF. It stands for Reduced Row Echelon Form. If you do this in a calculator, you can solve the system. And if you solve it, you wind up with something that looks like this. 1, 0 underneath, a 0 up here, a 1, and then I think this is like -1/3, and this is 4 down here. And so what this equation, or excuse me, what this matrix is telling us is the same thing it was telling us before, two equations, two variables, and what they're equal to. In this case, it's just saying x plus 0y equals 1/3, and this is saying 0x plus 1y equals 4. So it's really telling us the solution. It's saying that x equals -1/3 and y equals 4. That's our solution. So by using this matrix manipulation, we can go from the set of equations into a matrix and then manipulate the matrix to get a solution to our system of equations. And that's pretty handy. But this process for us, it's not going to be that useful. We're not going to be doing a lot of matrix manipulation, but we are going to be using matrices to represent systems. So if you think about this, this set of equations up here, we can also write our matrix equation, or we can write this as a matrix equation in another way. I can write it like this. I can say 3, I got to scoot this up just a little here, 3, 2, -6, and 1, I'm going to write it like this, and then I'm going to multiply that by another matrix that is x, y. And that's going to be equal to 7, 6. And so looking at this thing, you might look at it and go, wait a minute, I can see where the 7 and the 6 come from, and I can see where those numbers come from, but how is this x and y kind of a separate thing? Well, because what we're really doing is we're writing a single matrix equation, and this matrix equation is made up of a series of 3 matrices. This one times this one equals that one, and this one right here we would call a 2 by 2 matrix. And you can probably figure out why that's 2 by 2. It's 2 because there's 2 rows and 2 because there's 2 columns. And this one similarly would be 2 rows by 1 column, so this is a 2 by 1 matrix. And so is this one. It's a 2 by 1 matrix. Now if you look at the multiplication problem, we're saying a 2 by 2 matrix times a 2 by 1 matrix equals a 2 by 1 matrix. And that's because the only way matrix multiplication works, multiplying 2 matrices together, the only way this works is if these 2 numbers on the inside are the same, right? So this could be a 5 by 2, and that could be a 2 by 18, and it would still work as long as these 2 numbers right here are the same. And the result, what you get as a result, is what those 2 outside numbers are. So you'll notice this is a 2 and that's a 1, and that's where we get our 2 by 1 over there. And so matrix multiplication, for those of you who've never seen it before, it's kind of a weird looking thing, but it's an operation that allows us to take one set of 2 equations like this and turn it into a single equation. So this one equation represents the entire system. So one equation represents the entire system. Oops, the entire system. Squeeze it together, right? And they have fancy names, like for example, we would call this the coefficient matrix. And you can probably tell why it's the coefficient matrix, because of course those are all the coefficients of the variables up here in the original equation. And this right here, because it's just one column, and it's technically with variables in there, we would call this a column vector. And yes, vectors and matrices are deeply connected. And so we can do the same thing with a system of differential equations. So I'm just going to write down here, we'll do the same with a system of differential equations. And that's what we're going to be spending a little bit of time on. The only catch is that when we start talking about vectors and things like that, and matrices, things that we're going to refer to as matrices, we're going to use a special notation. And there's a couple of different ways you can do this. If you're familiar with vector notation, sometimes you know they draw a little arrow over the top of things. But we're going to represent matrices with capital, bold letters. Right? And that's just the notation that we're going to use. So for example, we might rewrite this equation right here as capital A, and I'm going to make it bold, but just by darkening it, A times this guy right here we could call capital B equals the result matrix right here, 7, 6. Now you could say it equals C if you wanted to, but the B in this case, if you remember, that represents that's standing in place for our variables. And this was our coefficients. And they just so happen to equal the column vector. Now, we didn't talk too much about how to go about getting that multiplication, that make that multiplication work, but you could probably figure it out just kind of by process of elimination. That if we start with a 3, a 2, and we got to have our original equation was 3x plus 2y, you can see that you take these numbers values right here and you multiply them vertically by this guy right here. That's why those two numbers have to be the same. The number of rows has to equal the number, or excuse me, the number of columns here has to equal the number of rows for this guy here and here. So the 3 times the x gives me 3x. The 2 times the y gives me 2y. And the same thing could be said if we decided to use the other row. We could say this row, but since there's no other column, we just kind of do the same thing, the same column, and say negative 6x plus 1y. And that's where our equations kind of can be reformed from. So matrix multiplication, we're going to get into a little bit more in the later on here. But just for starters, that's how we're going to be able to start with an entire system of differential equations, but write it as one single equation. So let's take a look on the next page and see how that might work with our old pal, our predator-prey system from section 2.1. Now you look at this thing and you realize, oh, we have two equations. So how is this going to work? Well, we can just as easily on this side, we can say, oh, that's two things, that's two separate things. So I'm going to write this in matrix form as one column matrix, which is going to be dr dt on top, and the bottom would be df dt. And that's going to be equal to, because the equal sign's still there, and then this thing I need to be able to write in matrix form, and the simplest way is to say, I think it's negative 2r minus 1.2 rf, and on the bottom it's minus f plus 0.9 rf. Now you'll notice I haven't split it up, it's just one matrix equals another. But I've gone from two equations to one single equation just by grouping things together. Now, what we'd like to be able to do is write it like this and say, oh, it's got to be equal to some matrix A times our variables, Rf. The question is, what is that coefficient matrix? What do these numbers have to be? And of course, the answer for us right now is, I don't know. You can tell pretty easily that I can't just make it as simple as a negative 2 and 1.2 because this has an r in it and that has an r in it. So this one's actually pretty complicated. This one's not going to be so easy for us to write. But for the time being, we've been able to go from two equations into a single equation just by using matrices. And so we're going to take a look at a slightly simpler system to kind of pick it apart a little bit. And so if we have our system of equations, we can rewrite that into our matrix equation. So we'll call this dy dt and then dv dt. And so that'll be the left-hand side of our equation. And the right-hand side is just the matrix, column matrix, v up top and minus y in the bottom. So that is 100% a rewriting of this system of differential equations into a single equation. Now what's nice about this is it allows us to, this one's pretty easy for us to do. I can kind of pull this apart or rewrite it slightly and write it as 0 times y plus 1 times v, and you'll see why I did that in a second. Down here it's negative 1y plus 0 times v. And now, with a little bit of intuition, I can pull this part one more time and actually write it as a coefficient matrix times my variables. And so pause for a second and think about what would your what would your coefficient matrix have to be? It's got to have 1, 2, 3, 4 numbers that when I multiply it through my y, v, should produce the exact same equation back. So hit pause for a second and see if you can think it through. It's not terribly complicated. It just involves some zeros, a 1, and a negative 1. Okay, so if you've thought about it for a second, maybe you came up with it. If you didn't, it's no big deal. In this case, it's going to be 0, 1, and then down here, negative 1 and 0. And just to convince yourself as to how that works, remember we take that top row and multiply it by this column and get 0 times y plus 1 times v. Sure enough, that's just v. And in the bottom, we do the same thing. The bottom row, negative 1 times y plus 0 times v. And so kind of following that same pattern here, just gives us negative y in the bottom. So this multiplication of two matrices produces this. So if we write dy dt, dv dt equals this multiplication, we've now written our matrix equation that represents the system of equations as a coefficient matrix times a variable matrix or a column vector. And if we substitute specific values in for our y and our v, we can actually find out something interesting. So for example, if we started with the equation that we know to be true, our matrix equation, so dy dt, dv dt equals, I'm going to kind of scooch this and condense this equation, equals just these coefficients, 0, 1, negative 1, 0, times whatever values we want to put in for y and v, or whatever conditions we want to give it for y and v, we can plug in values and see what happens. But I don't want you to think of this as plugging in values that are just kind of randomly chosen. What we really have is our coefficient matrix times this guy right here, and this really does represent coordinates on the phase plane. So if you give me any y and v coordinate that's on the phase plane, I can tell you something about it. And specifically what that's going to give me is it's going to give me the vector value. Remember that v stands for vector value at whatever coordinate you're interested in. And so this is going to give me the vector field value over the y and v scalar functions. Another way of saying it, if you give me a pair of coordinates on the phase plane, I can tell you what direction the phase plane is going to be pointing. Right? What's the slope, basically? You can think of it that way. So what we're going to do now is we're going to come up with 3 examples, and I'm going to have you hit pause in a second, and let's figure out what is the vector field value at coordinates 1, 0. We'll work that one out. And then what are the vector field values at coordinates 0, 1? We'll keep it simple for the first two. And then for the third one, we'll do something a little bit more complicated. What's the vector field value at negative 2, 2? So I want you to hit pause and figure those out. I'm going to hit pause. I'm actually going to fill them in so you don't have to watch me write them. But hit pause and see if you can figure out what is that telling you. So hopefully you had a chance to do the calculations. They're not terribly difficult calculations, but rewriting this as the matrix multiplication, you can see that our coefficient matrix times our conditions, y and v values, produce something that looks like this. And what we're seeing right here is the output, the vector value of that particular y and v location. So it's literally saying that when y equals 1 and v equals 0, then dy dt equals 0, because of course all this is equal to dy dt and dv dt, and dv dt is equal to negative 1. So that's a literal translation of what that vector, what that matrix is telling us. Another way you might say this is on the yv plane, on the yv phase plane, at that point, the vector field points And what direction would this be pointing? Well, it would be going 0 in the horizontal direction, and it would be going -1 in the vertical direction. So it points down. That would be another translation of what that means. Now take a second and see if you can translate what these other two mean as well. I'll write them in, but go ahead and hit pause. So the second one you might read as, at the point 0, 1 on the phase plane, the vector field points directly right, because that's 1 in the horizontal direction and 0 in the vertical direction. So that's kind of the textbook definition of right. And then down here for this last one, if you're at a point -2, 2 on the phase plane, the vector field points, well, what does that mean? Well, it means it's going right 2 and up 2. So it's going right 2 and up 2. And so you might call it up and to the right, but really that is giving you the components of a right triangle, right? And so if you imagine this thing is going to the right 2 units and up 2 units on the phase plane, then the result, or the resultant of these two vectors, this right here, has a direction, you call it 45 degrees, but it also has a magnitude of the square root of 8, or 2 root 2. Right? And you can get that just by using Pythagorean theorem. So a squared plus b squared, it has to equal c squared. And so that magnitude has got to be the square root of 4 plus 4, or the square root of 8. So that's what this this equation is really telling us. It's giving us all the information in a condensed form and allowing us to kind of predict what's happening on the phase plane. So we'll stop the video here and we'll continue on in the next one.